So today we're going to be talking about mass transfer and diffusion. As you see, we have a diagram here filled with a tank of a species in which we're going to use out to test our equation today. So eventually, over time, these particles will fill up the tank. So as you see, we have T0, T equals T1, T equals T2, and T equals T3. And then we have a fluid at the very top of the tank that will eventually move down as eventually those times go up. So as those particles fill up the tank, time eventually continues to keep going. So once eventually the fluid comes down all the way to the bottom of the tank, it covers up all of the tank, which equals zero, which equals the equilibrium state in which our particles have. From mass transfer, it would be a mass transfer from a higher concentration to a lower concentration. A net mass transfer equals zero because it is uniform. And also a transfer rate proportional to the area because it is cross-sectional area in which we're trying to solve. All right, now we're going to talk about three different fluxes in which we use to find out for our mass transfer or for diffusivity. First, we have a momentum flux, which is shear stress. Shear stress equals the momentum over du over dy. This is Newton's law of viscosity. Next, we have the heat flux. Q, which is the heat flux, equals negative K, our thermal conductivity over our thermal conductivity times dt over dx. This was Fourier's law of heat conduction. And then lastly, we have molar flux, a binary mix of A and B. It is represented by J, and the equation is JA in the direction of Z minus DAB, which is our diffusivity, times dCA over dZ, which is our concentration gradient. This is Fick's law of diffusion. Our JA in the direction of Z is our molar flux. Now we're going to start deriving our mixture. Our molar average velocity. Vm equals the sum of velocities times its component of Ci over the concentration equals N divided by C, which equals Na plus Nb divided by C. This equals our total molar flux for A and B. So now we're taking the flux of A, which is Va and Ca equals L divided by T times mole divided by L to the third equals mole times L squared times T, which equals our flux. This is our mole per length squared. Now we're going to look at the duration of our mixture to expand it. So Vm equals the velocity of A times the concentration of A plus the velocity of B times the concentration of B over C, which is our total concentration. Now it's going to give us XA, which is the mole fraction of A times the velocity of A times the mole fraction of B times the velocity of B. So now we're going to go down to our diffusivity velocity of our species. So Vi naught equals Vi minus Vm, which is our mixture, which equals Ti over the concentration of Ci, which is also, you can write as Vi equals times the concentration of Ci equals Ni. Again, this is our diffusivity velocity of species. All right, lastly, we're going to look at our stationary coordinate system. As we look at the equation, Ni equals the concentration of Ci equals Ji over concentration of Ci plus Na plus Nb divided by C. And we go back to that is our molar flux. So now we're going to take the derivative of Na and Nb. So now the negative concentration of DAB times the derivative of XA divided by dZ plus XA is going to give us our first derivative for the A value. Now we're going to look at Nb. the negative concentration of dBA this time, and dXB over dZ plus XB will give it our derivative of MB. And then once you simplify all of it algebraically, you get Na equals Na over the area, which is our molar flux in simplified terms. Alright, so today we'll be talking about our equimolar counter diffusion, known as EMD. So let's say we have two tanks filled with two species, tank 1 and tank 2. They're both a closed system. We know that the temperature is constant, our pressure is constant, and C is our concentration is constant. It's a closed system, so there should be no entry for anything to contaminate our species. It has two entry points as well. We know that YA1 and YB1 is our mole fraction, and we know that YA2 and YB2 is our other set of mole fraction. We know that YA1 is greater than YA2, and we know that YB2 is greater than YB1 as our mole fractions. And then, since it's a closed system, we know that our total net flux is 0 because both tanks meet up in the middle directly even in proportion to diffusive flux. So now we know that we have our tank perfectly labeled and drawn out. We're going to go down to the diffusive and get into the derivatives of this EMD. So we know our molar flux of A equals the negative concentration of DAB, which multiplied by the derivative of XA divided by the derivative of Z, plus XA again times by N. Again, we know that this is the net molar the net molar of A and the diffusive flux. We know that our net flux equals Na plus Nb equals 0. So taking that means that Na will equal JA, and then Nb will equal JB, the flux of A and the flux of B. Again, we know that our temperature is constant, and our temperature is constant, and our pressure is constant. So now we're going to go ahead and solve our derivative. So when you go ahead and take the equation over it, you're going to get the concentration of DAB multiplied by XA1 and then X of A divided by Z minus Z naught, but Z of I. Once you get that, that'll give you the steady state equimolar diffusion, which we will use. Also, we know that with that, D of B, dA of B equals negative dB of A, because they're the complete opposites. So we're going to know that to get dAB, we're just going to need the opposite, which will be negative dBA. And then we know that concentration equals the concentration of C of A plus the concentration of B to get our total concentration. So now lastly, we're going to take the differential of our constant. So we know our differential of C, which is the constant, equals 0, which goes back to equals the derivative of the concentration of A plus the derivative of the concentration of B. We know that the derivative of the concentration of A is equal to the negative derivative of the concentration of B, which also goes back to equal that J of A equals negative JB. So then when we solve that, we're going to know that J of A equals the negative derivative of A and B multiplied by the derivatives, the concentration of A divided by Z, and then we know that the JB, which is our flux of B, is going to equal the negative derivative of B of A multiplied by the derivative of C and the concentration. So now lastly, we have once you're able to derive the concentration of A and the concentration of B, you're going to get a derivative of dA of B, which is equal to the derivative of B of A. Knowing that they're both similar and they're both equal, that you can be able to just cancel them out and get that you will get our both derivative of both areas of A and of B.
It's static or non-diffusing, so we have no flux of B. Therefore, total flux equals that of NA. Now, to rearrange our equation and manipulate our equation to something that is solvable, we have the flux of A in the Z direction equal to that of the negative concentration times the coefficient of diffusion over the new bulk flow times our gradient. And we know that we have NA by itself now because NB equals 0. We will now try to combine like terms. On our third equation here, we're now simplifying even further. We have moved our differential of Z over, and now we're left with the concentration, the coefficient, and our gradient. We know that N equals out, so we know that the total flux of AZ in is the total flux of AZ out. So we now know our change in flux with position has to be 0. Manipulating even further, we know from Z2 to Z1, we also know our mole fraction from position 2 and 1. From there, we bring out our Z's, and we now can make our log of our gradient. Our final equation is that of Z2 minus Z1 to the other side of the equation, giving us our final equation of the flux of AZ in a unimolecular diffusion.